1.3. Sources. Okay, so sources, also known as supplies, supply power to a circuit. There are two primary. Oh, no, wait, I'm on the wrong one, aren't I?
Yeah.
Yeah, you guys are like, oh yeah, we're doing voltage dividers. It's like 1.3, we're not there yet. All right, voltage dividers, 1.2. So in chapter 2, we're in chapter 1 still, we'll learn about how to approach circuit analysis in a systematic way. For now, we'll limp along unsystematically with our tool belt of concepts and equations in order to introduce some more circuit elements, concepts, and theorems. But we can't resist just a bit of circuit analysis now. And so let's look at that circuit that we're going to analyze, the voltage divider, which is a ubiquitous and useful circuit. In a sense, it's less of a circuit and more of a concept, which is a little bit sarcastic, but is kind of the case. So for resistors, that concept can be stated as follows. The voltage across resistors in series is divided among the resistors. You kind of knew that, I think, hopefully. But it's just sort of an observation that we can make use of if we want to change the voltage that we have. So say we've got 10 volts, we might want 4 volts. It's pretty straightforward to use a voltage divider to get there. If you have 10 volts and you want 20 volts, not as easy, but you can't use a voltage divider at least. An immediately useful result, though, is that we can divide voltage into any smaller voltage we like by putting in a couple resistors. In order to show how the voltage divider divides up the voltage, we must do some basic circuit analysis. Consider the circuit in figure 1.1, which is this guy here. Two resistors in series. We have the voltage from the top to the bottom being defined as the input voltage, and the voltage across resistor 2 being defined as the output voltage. So that's our really basic circuit. The input voltage, Vin, is divided into the voltage across R1 and the voltage across R2, which we say is our output voltage. We want to know what the output voltage is as a function of the input voltage. And you can also have parameters like R1 and R2, but you don't want things like the current through resistor 1 in there in your equation, because that's not a known quantity, at least yet. It's not a known quantity. You could solve for it. So let's write down the equations we know from the laws of Kirchhoff and Ohm. So what is Kirchhoff's voltage law for resistor 1?
The summation of current and any junctions equal to 0.
Yes, although I asked you for Kirchhoff, but let's come back to that one. Let's do Ohm first, because that's what I wrote first. What is Ohm's law for resistor 1? VR1 equals what? So IR1, the current through R1 times R1. Okay? And let's do Ohm's law for resistor 2. What is that one going to be? VR2 equals what? Okay. IR2, R2. Good. Now let's do Kirchhoff's voltage law. So looking at Kirchhoff's voltage law, what we really want to know from it is how to write. Well, we've already written that V out is equal to VR2, which kind of used Kirchhoff's voltage law for that in a really limited sense. Really, when we use Kirchhoff's voltage law, we should put signs on, right? So plus, minus, plus, minus. We could have chosen plus and minus to be anything, but we chose it to be that way because top to bottom being drops is pretty typical to see. We'll talk more about signs later, but for now, that'll suffice. So what can we say that V in is equal to in terms of VR1 and VR2? The sum, yeah. So it's just VR1 plus VR2. Now what if I had changed the direction of the plus and minus on R2? It would have been negative R2. But since we put the drops in the same direction, we could just add them. Because we like plus signs. They're better. Okay, it's a proven fact. Okay, so now we have one more law we can use to get one more equation here. Any ideas?
Kirchhoff's current law?
Ah, yes, Kirchhoff's current law. And what was it going to tell us about the currents here?
They're all the same.
That they're equal. IR1 equals IR2. Now, what would this have come out to be if we had switched the signs plus and minus?
They would still be negative.
Yeah, there would be a negative sign here. But, yeah. All right, so I'm going to call all of these equations star, okay? So these are going to be like star A, star B, C, and D, but I don't want to write them. Okay. So we've already established that the output voltage is just VR2. So we can solve for VR2 in terms of these four equations that we have above. We want to eliminate the three unknown variables, VR1, IR1, and IR2, right? Since we have four equations, we want to solve for one of the unknown variables, VR2. There are three others that are unknown. We could solve for all of them, right? Four equations, four unknowns, they're linear. We could do this. You've spent many years of your lives solving for unknowns in systems of equations, right? Yeah. So we could do it, but we actually only care about VR2, so that's all I'm going to go for, is just unsystematically solving for VR2. So we begin with the second of the start equations and proceed by substituting in the others. So the second one was Ohm's law for the resistor 2, VR2 equals IR2, R2. IR2 is equal to IR1, right? So let's use that equation. So IR1, R2, and IR1, there is a formula for that. There's an Ohm's law here with IR1 in it, so let's use that one. Notice that I'm doing this just by feel. I'm just substituting. This works for simple problems. But when you get a system of more equations and they're more complex, you aren't going to want to do it this way. That's why we're going to learn a systematic way later. For now, we're just going to march ahead. So IR1 is equal to VR1 over R1, which gives us R2. Since we have an R1 in the denominator, just pull those both out, and we get VR1 there. Then our VR1 is in an equation we haven't used yet. Typically, when you do these, you're going to want to try to use all of the equations that you have and not reuse them, at least not until you've used all of the others. That's like a general rule that helps. So VR1 is equal to Vin minus VR2. So let's plug that in. Over R1. Vin minus VR2. And so R2 and R1, those are parameters. We don't need to get rid of those, right? Vin, that's what we want in the answer, right? We want to know what V out is in terms of Vin, so that's good. VR2, that's what we're solving for. So now it's on both sides of the equation. So let's bring it over to the left-hand side, this term, so that we have, and I'm going to factor it out at the same time, you guys. I know. It's a lot. times VR2 equals what's left over here, which is R2 over R1 times V in. Okay, now we're going to divide over that big old term, VR2 equals. We'll put the R2 over R1 in the numerator, and then we'll divide by 1 plus R2 over R1. All of that is multiplied by V in. We can simplify this by dropping R1 into the denominator and multiplying it through, which gives us R2 over R1 plus R2, because the R1's cancel in the second term, times V in. It's a pretty simple expression when you get down to it. So we can write the input-output relationship for a 2-resistor voltage divider. So we've got that V out is equal to VR2, and we just solve for VR2. So we've got it. Whoops. V out equals R2 over, come on. It's like technical difficulties today for some reason. Times V in. Boom. Nice. So the voltage divider had the effect of, you guessed it, dividing the input voltage into a fraction governed by the relationship between the relative resistances of the two resistors. So it's going to take values from 0 to 1, right? So if R1 is 0, or if we could say R2 is much greater than R1, this is going to be approximately 1, this fraction, right? So the output voltage will be the same as the input. If, on the other hand, R1 dominates and R2 is relatively small, then this fraction is closer to 0, approaches 0 in the limit, and we have 0 output voltage. So you pretty much are given a knob by choosing your 2 resistances for how much voltage is going to come out. Kind of nice. So that's like a handy little circuit for dividing voltage down. But we are not going to want to go through that little circuit analysis. It was easy, right? It was an easy circuit analysis, but it still took us 10 minutes probably to go through it. So we don't want to do that every time. So let's just commit this formula to memory by just remembering that the output voltage is going to be the same as the input voltage multiplied by this fraction, which is just the resistance of the resistor the output is taken from, divided by the sum of the resistances. So if you can just remember that. I mean, I don't like memorizing, and like this one is important enough to memorize, because I also don't like rederiving that formula every time either. But it's up to you. If you want to rederive it every time, I mean, might be a little slow on an exam, but you might be just super fast in general. So, it's up to you.
Question.
Yeah.
The steps above.
I'll back up here.
Yeah, the
Mhm.
one. Yeah, from where it's come. The 1 plus R2 over R1.
Yes.
Yeah. The one.
Oh, where'd the 1 come from?
Yeah.
It came from the fact that we had a VR2 on this side already, and we added
Oh, okay.
this R2 over R1 VR2 term over. So then there was a VR2 and then an R2 over R1 times VR2. So we factored out the VR2. Yeah, I did a couple steps there. And I'm going to start doing fewer and fewer steps, but I know that summer just happened, and algebra sometimes is a hard time coming back into our minds after the summers. So, yeah. But I'll start skipping steps a lot. But check me, though. Check me, because I will I'm often wrong, but never in doubt. Okay, so similarly for n resistors in series, so we just did 2, but we could do n with a very similar process and show that you can get an output voltage, V out, as being the resistance across resistor K. So I should write up here, for output across RK, you get RK over the sum of all the R's. So R1, R2, all the way up, including RK, so I'll put RK in. And then technically I should do more ellipses to Rn. Holy cow, that was a long fraction. Okay, did we do it? We did it. Okay, times V in. Or we could have just written VK, but I didn't in my notes, so I didn't do it here. Okay. Okay, any questions on voltage dividers?
Why is it that we can consider V sub R2 equal to V sub out?
That was just a decision that we made when we drew the circuit.
Okay.
We could have chosen the output voltage to be R1. It really wouldn't have done us much good to choose it to be the same as the input voltage because we wanted to change it. The idea would be that we're going to use this circuit. Say we had a battery. It was like a 9-volt battery. So you had like a 9-volt plus minus battery connected up. Whoa. Connected up to this guy. And you're like, if you can draw a straight line, there we go. You're like, okay, I want to get out 5 volts. So I'll put these resistors in here and figure out what their ratio needs to be so that my output voltage here, I'm going to connect this to something. So maybe I'll connect this up to some load. I want like to deliver a certain voltage across some load over here, and that load will then see, I mean, if this has any resistance that's not significantly larger than R2, it's going to draw the voltage down even more from there. But at least it starts out, we'll talk more about drawing down voltage, but it starts out at, say, 5 volts. Say you wanted 5. So if you wanted that, you could use the formula right here, and you want to know what your relationship between R1 and R2 is. You want your V out over your V in, which you just divided over, to be 5 over 9, right? So then we know that R2 over R1 plus R2 should be equal to 5 over 9. And we have 2 unknowns in one equation. You have to specify one. Okay. So say like I want R1 to be 1 kilo ohm, and then you can solve for what R2 should be to make that happen. So that might be an application. Okay. Voltage divider. We feeling good about it? I feel good about it. Like I've done this several times. So, okay, good.